This video gives you the solution to the activities in the slides on hypothesis testing. Start by this question, which is on slide 16. So you have the mean weight of adult women in the US is 140 pounds with the standard deviation given here. You are willing to accept the report of standard deviation, but not the mean. You selected 400 women, so you know that the sample size is large. That's one of, remember when you're doing a question on hypothesis testing, you need to look at the sample size and whether the standard deviation from the population is known or unknown. So in this particular context here, you have a small sample size, and then if you read, there is only one place where the standard deviation is given. This is where the standard deviation is given. And this then standard deviation is not the standard deviation of a sample. It is not the standard deviation of a sample because if this were the case, it would have given you the standard deviation related to the 400 women. But this standard deviation has nothing to do with the 400 women. So obviously this is the population standard deviation given to you, which is sigma. And then you are given the average from the sample, which is x bar. So given all these different information, then you can work it out and do this question. Test at the 5% level of significance where the true weight, the true mean weight is 140 pounds. In fact, it is a true mean weight, is 140 pounds. So to be able to do so, remember the information that you have here. You are given the true mean, you are given the population standard deviation, which is sigma, you are given the sample size 400, which is large, and x bar 137 pounds. From there, you will be able to start, remember all these different steps in hypothesis testing. You will start by defining your term. So let me just write it down in a different ink color. When you have defined your parameter, the next step is to define your hypothesis, as we know. Remember that in this course, we are dealing with only a simple null hypothesis, right? So this is going to be equal to 140 because how do I know this is equal to 140? It's all about what is asked in the question. It's asking you whether the true mean weight is 140 pounds. So the only way to do so is to make it equal to 140 pounds. Then versus not equal to 140 pounds. Why not equal to? Because it depends on what is asked in the question. The question asks whether the true mean weight is 140. So whether it is equal to 140, this is what we have. But the fallback of this is of course not equal to. We don't put greater, we don't put less or anything like that. It is not equal to. That is the fallback of 140 of the true mean weight being 140 is that it is not 140. This is why I put this way. When you have done your hypothesis, when you've set your hypothesis, the next step is you need to state whether your level of significance, right? You need to state your level of significance. And you also need to say what type of test you're carrying out. Here you're carrying out a two-tailed test because it's not equal to. And don't forget the level of significance. When you've done that, the next step is to state any assumption that is required. Since here we are dealing with a large sample and sigma is known, there is no specific assumption to do here except the assumption that works in almost all situations, which is the assumption of randomness. But in this particular question here, you will see that it's already mentioned that you've selected 400 women at random. So basically in this particular context, there is no need for you to write the assumption at all. If you were to be given marks in exam, you would not lose any mark if you don't write anything here. But just for the sake of completion and for the sake of revision, whenever you have to go through other questions, you might recall that I told you that if there is no particular assumption to do, there is this assumption of random sample that you can apply everywhere. But here, as I said, this is not necessary because you already have information that has been taken at random. Just for the sake of completion of these steps, I'm going to write it down for you to be able uh, to remember these steps well. Under H note, don't forget this because all your hypothesis is based on H note. All right. Under H note, we are going to write down what the distribution of our test statistic. The distribution of our test statistic is X bar, which is our point estimate, minus mu divided by, here you would have to write either s over root n or sigma over root n. As I said, if you put s over root n, you are wrong because this is not s that is given, but sigma. This is the population standard deviation that is given. So do not put s here. And then obviously, given that this is a large sample, according to the central limit theorem, which we explained last time, we know that this x bar is going to follow a normal distribution. So because here we are dealing with the standardized version of x bar, this is why it follows a normal with mean 0 and variance 1. So this test statistic follows a standard normal distribution. So the next step, of course, is to do the calculation. And given that this is obtained from a normal distribution, sorry, that this is obtained from a normal distribution, that's why I put z equal. I gave it the name of z. So we're going to include all these different values. X bar is 137 pounds. Minus mu. What is mu? Mu minus mu. What is mu? Mu under H note. Under H note, mu equal to 140. So I put subtract 140 divide by sigma over root n. Sigma is 20 divided by square root of n, which is 400. And we're going to compute this, which is equal to minus 3. All right, you can do the computation later on. You will see that it is equal to minus 3. It's relatively easy anyway. So root of 400 is 20 over 20, which is 1, minus 3 over 1 is minus 3. Next step is to state your rejection region. To state your rejection region, we will write down if, in fact, because it is a two-tail, that's why I'm going to put the modulus z here, all right? Otherwise, there was no need. Just refer to what I explained in the lecture last time. With regards to the two-tail, you have a modulus z. And then it's greater than what? If it is a 5% level of significance from a normal distribution, please refer to the lecture. You would remember that it was 1.96 that the value is. So I'm not going to go through it again because we've already discussed that. So remember that it is z greater than 1.96. Each time that you are dealing with a 5% level of significance on a two-tailed test from a normal distribution, it's always going to be 1.96. If it was a one-tailed test at a 5% level of significance, it would have been 1.645. You could check it out later. But here, for a two-tailed test from a normal, a for a two-tailed test from a normal, with 5% level of significance, it's always going to be 1.96. It won't change. You won't need to even go and check in your table each time because it's going to be something standard. So if modulo z is greater than 1.96, reject H note. And then we do the conclusion since modulo z equal to the modulus of z is equal to what? Modulo z equal to 3 because we have z is negative 3. So modulus of negative 3 is 3. And 3 is what? Does it go according to this statement? Yes, it goes according to this statement where it is greater than 1.96 as you see. So what do we do? Since modulo z is equal to 3, greater than 1.96, what do? We shall reject the null hypothesis at the 5% level of significance and conclude that. Don't forget, in all your conclusions, it's going to be technical first, and then it goes into um, the answering the question itself. So, what was the question? Test at the 5% level of significance whether the true mean weight is 140 pounds. So, your conclusion is that since it is greater, we rejected the null. The null says that it is equal. Because we have rejected the null, we are saying that it is not equal. And conclude that the true average weight of adult women US is not 140 pounds. So that is all for this question. We move on now to the next question, which is slide 18. So here we go. Most water treatment facilities monitor the quality of their drinking water on an hourly basis. One variable monitored is the pH value, which measures the degree of alkalinity or acidity. And a pH below 7 is acidic, one above 7 is alkaline, and one which is 7 is neutral. The water treatment plant has a target pH value of 8.5, right? The mean and standard deviation of 1 hour's test results based on 17 water samples. So you see here that 17 water samples means that the sample size is small now. And the moment that the sample size is small, you know that you will have to do the assumption of normality at some point in time. But we are not yet there. We need to know whether we will be able to use a normal or we will be able to use a t-distribution. So we're going to have a look at that. Based on the sample of 17 water samples, based on 17 water samples at this plant are 8.4 and 0.16 respectively. Does this sample provide sufficient evidence that the water is alkaline? How shall you know if the water is alkaline if the pH value is above 7.0? We're going to check all this out. First of all, we have our mean mu, which is going under the H node, which is going to be 7 because this is what we are going to test. And then we know that there is X bar, which is 8.24. And we know that this 0.16 is not sigma because it is the standard deviation based on 17 water samples. So the standard deviation here is S and not sigma. The sample standard deviation is what you are given. So at no point in time do you have any information related to the standard deviation except this 0.16. So in other words, which means that sigma is unknown and your sample size is small, which already indicates that you are going to use the t-distribution. You are going to use the t-distribution in a moment. So let's start by the first step, which is the definition of your term that you're going to use. So what is the term that you're going to use? Let mu, again, because you are still testing the mean, be the true average pH value in water. This is what it means. Let mu be the true average pH value in water. And then you're going to write your H note. It's equal to, remember that it's always going to be like that. H note is such that mu equal to, and then H1 will depend on what is being asked in the end. So let's have a look. What is the question? I repeat, to know how to state your hypothesis, you need to know your question. Does this sample provide sufficient evidence that the water is alkaline? That is the question. It doesn't mention, by the way, any test of hypothesis or whatever it is here, but this question, by the way, could have been answered for a confidence interval, and you would have had the same interpretation in the end. But given that we are doing hypothesis testing here, we will still answer this question using hypothesis testing. And as I mentioned to you, if there is no significance level, you take it at 5%. So let's have a look. Does this water provide sufficient evidence that the water is alkaline? This is a sample. So the sample, how would you know if the water is alkaline? The water is alkaline if the pH is above 7.0. So you know that the mean should be 7.0 automatically. The next step is to get this one. What is going to be this one? If I put not equal to 7, excuse me, if I put not equal to 7, I will not be able to answer the question because the question is asking if the water is alkaline. But if I put it as not equal to 7, at no point in time would I be able to answer if the water is alkaline. Because if I reject the null, what I would be able to say will depend on what is happening in the alternative. If I put, for example, not equal to in the alternative, it means that if I reject the null, I would only be able to say if the pH is neutral. If I put it less than 7.0, then I will be able to say if the water is acidic, if it is not the null. So in other words, the only way to know if it is alkaline is by checking this to be greater than 7.0. The next step is to write down a two-tailed test is carried out as we mentioned. No, a one-tailed test, excuse me. A one-tailed test is carried out at the 5% level of significance. Or you could say at alpha equal to 0.005. All right. A one-tailed test is carried out at the 5% level of significance. Our next step is to determine if there is any assumption to do. All right, how would I know if there is assumption? Sample size is small and sigma is unknown. So if sample size is small, there is an assumption of normality that you can do. There is no need for you to write the assumption of random sample, but you can also do it if you want. There is no problem about that. So assuming that the pH level in water comes from normal population, don't forget this assumption, just like you would have done if you were to do this question using confidence interval. So under H node, then we'll start to write down our test statistics. So maybe what I will do to make things easier, I will just copy that or maybe there was no need for me to copy it because it's most of a waste of time rather than doing anything. Anyway, x bar minus mu divided by, the only thing that is going to change is s, because now you don't have sigma, but this 0.16 is based on your sample, and if it is based on your sample, it is s that is given and not sigma. And this follows not a normal now, because this time you have sigma unknown and sample size small. Recall from confidence interval that now it will follow a t-distribution, and we write this down like this. With a degree of freedom, which is n minus 1. We do write this in this way. And then the next thing is to calculate the distribution, the test statistic rather. And when you calculate the test statistic, we won't call it Z now, but we call it T, obviously. And maybe what I will do is, just to make things easier again, I'll just put this down there and then do the computation thereof. So the mean x bar is 8.24. Subtract the mean under each node, which is 7.0, divide by the standard deviation, which is 0.16, and divide by the root of the sample size, which is 17. We need to calculate this now. This is what I get. Now, just looking at this, it seems quite high, but we're going to check it from the T table. So we need to state our rejection region. Now, if you look at this rejection region, just try to understand it properly here, is that we are doing a test at the, we are doing a one-tail test now. One-tail test, as you see here, and this is on the right side of a distribution. So what are we going to do? Basically, what we are trying to do here is we will have a normal distribution, not a normal, excuse me, but the t-distribution, and given that it is a one-tail test, and what we need to do, it is a one-tail test, we need to find this critical value, as you would have noted. Given it is a one-tail test, this is the whole area here is on the right and not on the left, but it's going to be 0.05. So what you want to do is you want to find this value. Of course, we have a degree of freedom, which is n minus 1, which is 17 minus 1, which is 16. So the degree of freedom is 16. Okay, the degree of freedom is equal to 16. And then this value, which is on the right, is defined by Q, which is 0.05, as you would have seen. So let's go and identify that from the T table. So from the T distribution, what we're going to do is we are going to have a look at the normal, and then you have a T. Remember something is that, just said it, it is Q, the area on the right is Q 0.05. So we have 0.05 here in that third column, and then we have to match it with 16 degree of freedom. So here we go, 16 degree of freedom is 1.7459 with 0.05 as Q. So 1.7459. 1.7459. So any value that goes above 1.7459 is going to be rejected automatically. And any value less than that will not be rejected. So 1.7459 is our rejection region. All right, we're going to state it now. If t is greater than, you will see that now I don't write down modulus t because it's only one side. There we go. We reject that note. Then since t, which is equal to 31.945, which was obviously quite big, which is greater than 1.7459, which goes according to this region, rejection region. So we're going to reject the hypothesis. You can write down we reject H node also. Weigh the technical interpretation of the 5% level of significance and conclude that what? We conclude, does this water provide sufficient evidence that the water is alkaline? If we have rejected the null, it means that mu is greater than 7.0. If mu is greater than 7.0, it means that the water is alkaline. So, and conclude that the water is alkaline. Here we go. So now we have another question, which is here, which is for a two-sample case. This one is a little bit similar to what we have done, but in two samples. So we'll define our term. You can read through it. You already read through it. So we'll define our term, but the term here are twofold because you've got an average perception score for boys and you've got one for girls. So we will need to define it as follows. Let mu be and so let mu b and mu g be the true average perception scores of boys and girls respectively. Our next step, as usual, is to define our hypothesis. As I explained to you in the lecture notes, here we are comparing two different means because you are asked, is there a significant difference in the perception scores of boys and girls? So if you want to know if there is significant difference in the perception scores of boys and girls, what you need to do is to do minus mu b minus mu g equal to, excuse me, equal to 0, all right? Comma, not comma, but versus h1 is such that mu b minus mu g, and then we were gonna have a look at that in a moment. Minus mu g, we have 0 on the right, but we will see whether it should be less or it should be greater or not equal to. So, is there a significant difference in the perception scores of boys and girls? You see, in this question, it says, you are investigating your research hypothesis that boys hold more perception in this regard. Very good. So many of you might think that this should be greater than 0. But if you think like that, it's going to be wrong because at no point in time this question related to the uh, referred rather to the research hypothesis. It's just a question asking you if there is a significant difference in the perceptions of boys and girls. So if you want to know if there is a significant difference, you need to test for it to be equal to 0, and the other one would be the fallback should be not equal to, not equal to 0. It cannot be greater than 0 because of this research hypothesis, because the question is not about the research hypothesis. If it was related to the research hypothesis, obviously you would have put greater than 0 here, but otherwise, no. Now, for some students who are doing it mu g minus mu b, it's all fine. It's going to be the same thing. But if you were doing it greater, if you were doing it as greater for mu b minus mu g, now if you were to go mu g minus mu b, then it would have been less than. So this is the only thing that's going to be different. Otherwise, it's going to be the same thing. In the end, you get the same interpretation. So having said so, we are going to mention if a one tail or a two tail test is carried out. I think this one you got used to it. I'm just going to copy and paste this part here. All right. The 5% level of significance as usual, and then we're going to do our assumptions. So our assumptions of what? How do we know what assumptions we have to do in this particular question? Let's have a look at the sample size and let's have a look at the population standard deviation. Obviously, there is no population standard deviation here because these are the sample standard deviation. But what about the sample size? The sample size in both cases are large, 37 and 32. So if the sample size are large, there is no assumption of normality, no assumption of homogeneous variance, but there is one particular assumption that comes in, and this is the assumption of independence. This one will be always there. So we're just going to write this down. So we will assume that the independent samples of boys and girls were selected. Then you could also say, assuming that um, that independent samples of that a random sample that assuming that independent samples of boys and girls were selected and that they were randomly selected as well. Under H note, you might add the random selection, or if you don't want, there is no need, but at least the independent sample should be mentioned. Under H note, we can write down our test of hypothesis, test statistics, excuse me. So our test statistics is what? As usual, we would do x bar minus mu, but mu in this particular context is mu b minus mu g. And mu b minus mu g under H note is 0, so there is no need for us to write anything particular in subtracting mu b minus mu g. But we need to write x bar b minus x bar g. This is important. All right, x bar b minus x bar g. As I said to you, you will normally subtract mu b minus mu g if this was not equal to 0. But given that it is equal to 0, there is no need for you to do mu b minus mu g. So there's no need for you to write down minus 0 as well, because in the H note, mu b minus mu g would have been 0. This is why I don't write anything. I leave it as it is here. And then we're going to divide by the square root of, excuse me, square root of what? There are two things to consider here. There is one, the standard deviation for the sample of boys, and one for girls. So what we're going to do is that we're going to do s squared b divided by n, as I explained to you in the lecture, by the way. And then I'm going to do the same thing, but now with the girls. Sg and g. And this is going to follow a normal distribution because, of course, the sample size are large. Here we go. We're going to compute it as z equal to, and then we're going to put down these different values down there. Okay. So x bar b is what? 5.0 minus uh, x bar g. Here we go. And we're going to divide by s squared, which is s squared g, which is 10.2 to the squared, because here it is the standard deviation that is given, so you need to square it because it's the variance that you have in the formula. And the other thing, do not break down this formula into two different formulae, because the plus, you cannot break it down. If it was multiplied here, you would have been able to do so, but if it is an addition here, you can't do so. The NB is 37. We're going to do the same thing for this one. And this is equal to, I don't want to. So again, we already see that this is a big value, so there is going to be a rejection of H note, as you will note. So let's complete that. Since you don't need to put modulus now because you are dealing with only one. We are dealing with only one tail, a two tail. So yes, excuse me, we have to put. We are dealing with a two tail, so we'll still need to do modulus. Excuse me, just one thing to confirm in the above. So V above was done correctly with one tail test, but this one is a two tail test which is carried out. So if modulus set is greater, it's all again 5%. So if it is 5%, it's greater than 1.96. We check H note. If not, since if modulus z is greater than that, we reject H note. Now the next step is to do the conclusion. Since modulus z equal to 3.12 greater than 1.96, what do? We reject H note at alpha equal to 0.05. We reject the null hypothesis at the 5% level of significance and conclude that, what was the question? Is there a significant difference in the perception scores of boys and girls? So if the question is there a significant difference? So we have rejected the null, which means that it is not equal to 0. So if it is not equal to 0, it means that there is a significant difference, and conclude that there is. You can stop here, but I would suggest that you also give a direction in which there is. You say that there is a significant difference. It's always good to go a little bit higher than that, a bit deeper by saying, okay, if there is a significant difference, where do we have the difference? Is it that males or more positive perception, or is it that female or more positive perception? So this is the next step. And here we'll see that x bar g is less than x bar b. And you would have seen also that a the z value that you got is positive here. If the z value you got is positive, it means that mu b minus mu g is greater than 0 somehow. So if it is greater than 0, it means that boys hold more positive perceptions than girls, and conclude that boys um, conclude that boys hold more positive perception than girls, according to this particular context, obviously, and it depends normally on what we're doing, but here we have seen that boys hold more positive perception than girls. I'm going to take the last question. There we go. We're going to do the same kind of activity. We're going to reproduce what we have here, and then I'm going to just copy these three sentences because they're more or less the same each and every time. But then I'm going to do an adaptation, of course, according to the question. So let's copy that here and then let's discuss what is happening. So you have two class time, all right, and you are asked if class time is affecting performance. The only way to know if class time is affecting performance is based on whether the average score that student gets differ according to the class time. If the true average scores, if the true average scores differ according to these two different class time, then indeed class time affect performance. But if the average score does not change or the same, there is no significant difference in the average score. Therefore, you would say that class time does not affect performance. So what do we want to do? We want to say let mu1 and mu2 be the true average perception with the true average performance scores of 8 a.m. and 9:30 a.m. classes respectively. You will know that at no point in time did we mention any test of significance level. Did we mention the level of significance here? So, which means that this question could also be answered through hypothesis, through confidence interval, right? And normally you would have obtained the same interpretation in the end. The other thing is that given that we are doing it in hypothesis using hypothesis testing, we also need to know the level of significance, which is not mentioned as well here. So as I said to you, if this is not mentioned, you take it to be 5%. But this is the only way, either the hypothesis testing or the confidence interval are the two ways that you can go through this. So it's mu1 minus mu2 equal to 0 as usual. Mu1 minus mu2. Does class time affect performance? It did not ask you whether does 9:30 a.m. class perform better than 8 a.m. If this was the case, then what would have happened is that mu1, if you said that does 9:30 a.m. class work better than 8 a.m. So in other words, you would have said mu1 minus mu2 would be less than 0 because 8 a.m. minus 9:30 would be less. So, but in this particular context, it's asking does class time affect performance? So in other words, it's either affecting it positively or negatively, but in any case, it's not equal to 0. And then of course a two-tailed test is carried out at the 5% level of significance, and we are going to make the assumption now. What assumption shall we do? So as you would have noted that we are doing it to sample t-test, sample hypothesis testing on two samples, and in this particular context, the sample size for both groups, the 8 a.m. and 9:30 a.m. classes, are both small. So if they are both small, and obviously the variance that is given here is is the variance of a sample, and given that you don't have any population variance obviously, and you have two small samples, logically the t distribution will come in. But before you are able to use the t-distribution, you need to remember that there are three assumptions to do in the context of the a two-sample t-test. You have three assumptions to do, as we would have done in the confidence interval. So we're going to make these three assumptions. These three assumptions are independence, homogeneous variance, and also normality of populations. So let's do that. Assuming that the performance scores, I call it performance scores, you might have said it, you might have written marks, all right, it would have been okay, there's no problem. Assuming that the marks come from, I wrote it as performance scores. Assuming that the performance scores of 8 a.m. and 9:30 a.m. classes are independent, come from normal populations. Now you have S because you have two different normal populations, and that their population variances are equal under H note. So as you would have noted here, there are three assumptions to do. Assuming that the performance scores of 8 a.m. and 9:30 a.m. classes are independent, that's the first assumption, come from normal populations, that's the second assumption with S, don't forget, and that their population variances are equal, right, which is the third assumption that we did as we explained in the confidence interval. Then under H note, we're going to start writing down our test statistic. So what is going to be the test statistic? We'll see that it's going to be, I'm just going to write this down to make it easier for me, but I'm going to change this down there, don't worry. So it's going to be x bar 1 minus x bar 2. As I said, this doesn't matter whether you do x bar 2 or x bar 1, x bar 2 minus x bar 1, or x bar 1 minus x bar 2. That doesn't matter at all, right? It's all about the interpretation that you make in the end. The other thing is that this is going to be this is going to change a little bit here, because first of all you don't have NB, you have N1 here, and you have N2. All right, I think N1, you have N2, and then you will see that there is going to be one here. You will understand why I said that. It's going to be one here, and then just before that you have S squared P, right? S squared P. This is what you get. Normally you could say S squared is outside. You can take it outside, become SP over the root of 1 upon N1 plus 1 upon N2. Now, why did we do this part of S squared P? Because we have assumed that the population variances are equal, so we have only one sample standard deviation that could be used to estimate the single population variance that we have. Because they are equal, it means that there is only one population variance. So to be able to get that, we do the pooled estimated variance, and we know that this is going to be following a t distribution, as we already know, alpha, and then the degree of freedom this time is not going to be n minus 1 because we don't have n, but we have n1 and n2. So we're just going to be writing n1, hold on, going to write n1 plus n2 subtract 2. Right, the degree of freedom for a particular case is this one. Now, obviously, having said so, you see all these are things that you have gone through in confidence interval, obviously, right? I've already explained that in confidence interval, and I also explained how to obtain a t value, a critical value from a t distribution. So, but the next step is to do the computation of a t. But to be able to do the computation of a t, you will know that you need this s squared first. So we're going to write this down and calculate it first. So we know according to the formula that it is equal to, in the denominator, we have n1 plus n2 minus 2, which is in other words the degree of freedom itself. So we're just going to write this down here. N1 is 21 and n2 is 21 minus 2 in the denominator. And then we're going to write down the numerator. Remember that it is n1 minus 1 times s squared 1. So n1 minus 1 is 21 minus 1 times s squared 1. That is the variance for the first data, which is 196, plus n1 minus 1 times the variance 289, excuse me. And then in the end, we get with s squared p, we get 242.5. Obviously, it should be always in the middle of 196 and 230, 289, right? It should be in between these two variances. Now we can compute our t, which is equal to, and here we need to divide. What is x bar 1? X bar 1 is 78, x bar 2 is 82. 78 minus 82 divided by square root of, as I say to you, s squared p times 1 upon 21 plus 1 upon 21. This is what we have done here. All right, we have done s squared p 1 upon 21 plus 1 upon 21, which seems to give minus 0.832. All right, so we're going to do our statement of rejection region. If we have a two-tailed test, so if we again have modulus t, you would note, because it's a two-tailed test. All right, so let me just explain that from the slide here. So this, from the slide here, you will see that, just a minute, you have a t distribution and you have the zero value here because it is a two-tailed test. So you have two tails to consider in the t distribution, which means that this becomes 0.025 and this becomes 0.025. So what you just need to do is to find out what is this value. Remember that our degree of freedom is n1 plus n2 minus 2 which is in our example 21 plus 21 minus 2, which is equal to 40, right? So you need to look for 40 degree of freedom, and this value is our Q value in the T table. Otherwise, you would have to look at 95% plus 2.5%, which means 0.975 from the P value. So you just choose which one is appropriate here to find the T value. So Q 0.029 and a degree of freedom 40, right? Q is equal to, so Q equal to 0.025. You see 0.025 is here. Q is 0.025, and then you need to look for a degree of freedom which is 40. Just remember that column Q 0.025 or P 0.975, it's the same thing. And then um, you need to look for the degree of freedom which is 40. Just remember that part here, and the degree of freedom down there is 2.0211. 2.0211. All right, 0.025, 2.0211. Okay, so this is the 2.0211, which means that this is negative 2.0211. So what you have to say, if t is less than negative 2.0211 or t is greater than 2.0211, you reject H note, but as you would know, there is only one way. There is an easier way of writing this down. It is t modulus t is greater than 2.0211, right? So instead of writing this whole thing statement here, which is lengthier, you can write it down in compact form like this. If modulus t is greater than 2.0211, we reject H note. Let's do the conclusion. Since modulus t is equal to 0.832, because modulus t is the positive of a negative value here, which is 0.832. And does it go according to this statement? You see that 0.832 is not greater than that. If it's not greater, it is less than 2.0211. And if it is less, it means that we should not reject the null, obviously, because 0.0211 is where? 0.0211 is somewhere here. It's not in that rejection, it's in there. So this is what we just saw here. We just wrote here. If since modulus t is equal to that and less than 2.0211, we do not say accept, as I said. Never use the word accept. We do not reject H note at the 5% level of significance, and conclude that. So if we have not rejected the null, what does it mean? We are saying that the null is true, which means that mu1 is equal to mu2. So if mu1 is equal to mu2, what does it mean? Remember the whole reason why you did all this. If mu1 is equal to mu2, it means that the true average performance scores of 8 a.m. and 9:30 a.m. are equal. And if they are equal, it means that there is no difference in the performance of these two classes, right? So, in other words, the test performance, does class time affect performance? No, the class time doesn't affect performance in this particular case here. So, since it's not greater, it's less than, we conclude that class time does not affect performance. as it doesn't affect performance because it is equal to 0, which means that the class time of the first test, the first performance scores for the first class time is the same as that of the second class time, which means that class time has no impact on the performance scores here. So that's a little bit all that we had for the tutorial session.